Spoštovani gostje, dober večer. Lepo pozdravljeni na današnjem predavanju iz cikla Znanstveni večer Univerze v Novi Gorici. Danes bomo imeli predavanje dr. Saše Bajt. Predavanje bo potekalo v angleščini, tako da dovolite, da predstavitev izvedem v angleškem jeziku. So, dear guests, good evening. It's my pleasure to present today the lecturer and scientific evenings of University of Nova Gorica, Dr. Saša Bajt, especially because we studied together at physics, well, quite some time ago. She finished physics in University of Ljubljana, and after diploma she moved to Heidelberg, where she finished her PhD at Max Planck Institute under the mentorship of Professor Bogdan Pouch, and for that she got Max Planck Fellowship. And immediately after her PhD she moved to United States, where she worked at the University of Chicago in National Synchrotron Light Source, and later she joined Livermore National Laboratory in California, where she became a project leader developing high reflectivity and high stability multi-layer mirrors for extreme ultraviolet lithography. It's worth to mention that this was at that time the largest industry-funded research project in the history of the department, and definitely a very successful one. So the optics they developed under leadership of Saša Bajt enabled experiments with UV extreme light sources, flash, in Hamburg. So first diffraction experiments, and this is, I think it's something like pioneering experiments for the sources like free electron laser that are developed in many synchrotron radiation sources. So she was invited and moved to DESY to develop optics for this kind of extreme bright UV and X-ray sources. And now she's leading a group for multi-layer optics at DESY. So I should mention that she's, of course, a very successful scientist. She has over 130 scientific papers, in between also Nature and Physical Review Letters papers. She has 10 United States patents. And she received the NASA Group Achievement Award for outstanding research. And as interesting maybe that she's working also on interstellar material studies, if I understand properly, as a part of mineralogical research, mineralogy outside planet Earth. I think that she will tell more about her work during this lecture. We will hear about the breakthrough and what is possible today with optics and at atomic level with X-rays and UV. So I invite Saša to give the presentation on X-ray vision now and in the future. Please.
So thank you very much. Najprej bi hotela izkoristiti to priliko, da se vam zahvalim za uvodne besede in predstavitev in seveda tudi za povabilo, da lahko tukaj predavam, čeprav bo seveda ostanek predavanja v angleščini. So first of all, I would like to thank Professor Archon and also the university for the invitation. So I have been, I have visited Slovenia regularly, but of course I have never, it has been a while since I lived here, and it's really nice to see that places like this castle, for example, has been transformed into such a beautiful place to to use it for events like this to promote science and education. So in my presentation, I'm going to talk about X-rays and about how we use them to image and see structure on atomic and molecular level. I'll be also talking, of course, about X-ray optics, in particular optics that, well, multi-layer based optic, sorry, that yeah, is shown actually part of it here, and about their use in X-ray science. So maybe you saw there was a strange title of my talk downstairs, maybe because I'm also working on extraterrestrial materials, although that's my kind of side interest. Yeah, but definitely my title is actually X-ray vision, optics at the atomic scale, where X-ray vision actually has a double meaning. I want to say that we'll be talking about how do we see with X-rays, but also a vision what we will be doing in the future with X-rays. So let me start now with this slide, which shows a macromolecular machine at work. We are seeing here a macromolecular complex that acts as a machine and pumps calcium ions through this cellular membrane. So this is a process that's happening in every one of us. It's one of the processes that well, consumes lots of our energy. 1/3 of our energy goes into this process, which is related to muscle contraction and relaxation. So we contract the muscle. When we contract the muscle, the calcium ions are flooded on the myosin, which is a muscular fiber that does the work. And to relax the muscle, these calcium ions need to be pumped out into cellular reservoir. Well, if this doesn't happen for whatever reason, we'll get a cramp. The muscle can't relax. I'm sure that many of us experience that at some time. So this is just but one example of things that we can study now with the state-of-the-art X-ray crystallography, and we can see things on an atomic scale, molecular scale, and also follow processes like this. So at this point, I have to mention, this year is very special. 2014 has been declared by United Nations as the International Year of Crystallography. And this is to commemorate the centennial of X-ray diffraction. So X-ray diffraction was discovered, so to say, 100 years ago. But United Nations also wanted to make public more aware of the science of crystallography and all the technological developments that it enabled in our modern society. So basically all complex molecular structures that we know today have been discovered from the analysis of X-ray diffraction patterns. So many Nobel Prizes were given for solving the structures, like some of them are shown here. I believe more than 28 Nobel Prizes were given for solving such structures. And the solved structures are being accumulated in protein data bank. And you can see that their number is increasing exponentially here. Again, maybe because it's centennial of X-ray diffraction, people really tried very hard to reach the 100,000th mark, and actually this week it happened. The 100,000th structure was deposited in the protein data bank. So these protein structures are then available to everyone to study. You can also see that other methods are being used to solve such structures, such as nuclear magnetic resonance and electron diffraction. However, the vast majority is being obtained with X-ray diffraction. So the thing that I was just showing, X-ray diffraction, basically relies on the fact that X-rays are electromagnetic radiation with very short wavelength. However, when you mention X-rays to people, usually this is what they associate the X-rays with, which is another property of X-rays, namely that X-rays penetrate through matter, pretty much unobstructed depending on their density. This is also how X-rays were discovered about 100 years ago. So William Röntgen exposed a hand of his wife here and observed that on the photographic paper. You see that the tissue, which consists primarily of water and carbon, basically is not visible. It was transparent to these mysterious X-rays, while bones that contain calcium and a ring here, which is made maybe of gold, cast a shadow. So these are actually shadowgrams. They were immediately used by doctors to look for foreign objects in bodies, broken bones, and even today they're used pretty much the same way. Like dentists would maybe look for hidden cavities, or doctors would use them to look for maybe foreign objects in your body. And they are great because they allow doctors to see things inside your body without cutting it, so exposing it to bacteria and so on. But this is not the type of X-ray imaging I am talking about today. This is obviously not atomic resolution imaging. These are just shadowgrams. So basically X-rays consists also in the spectrum of our sun, for example. We see that, well, sunlight consists of different wavelengths, so we can see that typically very nicely in a rainbow. You see different colors, but what we see is just the wavelength region we can see with our eyes. Our eyes are adjusted for visible light, therefore we see just these rays. Well, sun emits also other radiation, practically all wavelengths in the electromagnetic spectrum. And here I'm showing some images of the solar corona taken at 3 different wavelengths, where these colors don't have anything to do with the color, visible color. I'm just trying to show that it emits light also in this wavelength regime. However, even if you would be able to see them with our eyes, we would never be able to see them on Earth. That's actually fortunate for us. And the reason is that this extreme ultraviolet radiation does not penetrate through the Earth atmosphere. Earth atmosphere acts as a very efficient shield for harmful radiation, such as extreme ultraviolet radiation, X-rays, and gamma rays. However, the electromagnetic radiation that I'm showing here, you see, has all kinds of wavelengths here. So normally this is our visible light spectrum, which is very narrow, that we see with our eyes, and X-rays have a much shorter wavelengths, about 1,000,000 times shorter than visible light. And it just happens that their wavelength is kind of comparable to the distances between atoms in matter, and that's also why we are able to use them to see things on atomic scale, because they are comparable to the wavelength of X-rays. So to explain how does this work, let us look at something maybe more familiar, what's happening like scattering of visible light, by scattering of visible light. So let us do an experiment where we have a slit that, well, is of the dimension of a couple of microns. So we shine a visible light on it, and we put the screen far away, and look, what do we see? And we see a diffraction pattern like that. So depending on how large this slit is, if the slit is much larger, then the pattern will become actually narrower, smaller. If the slit is smaller, the pattern will become larger. So let us take now 2 slits. If we have 2 slits, okay, we are dealing here with light, so the waves will start interfering. We'll get an interference fringe here. And depending on how far apart are these slits, we'll get finer or less fine pattern. And if the slits are closer together, closer than the wavelength of the light, visible light that we are using, we'll actually get this pattern, meaning we are not able to resolve anymore that there are actually 2 slits. So, and well, if you have 3 slits or 4 slits, whatever number of slits, the pattern, of course, will become more and more complicated. But the main point here is that this diffraction pattern that we see, this structure that we see, carries information of what did the light encounter, so what the interaction of light with this object that it encountered. So this is, like I was discussing this about the separation of 2 slits, so if they are getting closer together than the wavelength of the light, then we won't be able to resolve them anymore. This is also the explanation why can't we ever see with visible light atoms, basically, or We can't do atomic resolution imaging. So, well, we can take even more complicated thing, like let us say this molecule here, and shine a light on it. Yeah, then the pattern is even more complicated. But one very important principle in imaging is to realize that any object, no matter if this object is so complicated or if it's a crystal, so that it's periodic, non-periodic, or crystalline, or whatever, we can always deconvolve it in its spatial frequencies, Fourier frequencies. So we can always treat it as separate frequencies. What's happening with one frequency, let us say we take one spatial frequency, shine the light on this object, the object will act as a grating. It will diffract the light along these two paths, and we will see here on the screen, where the screen was now replaced by a detector, like a CCD camera, we will see 2 points. So then we take another spatial frequency, we repeat the process, and we'll get 2 points somewhere else, and so on. And we slowly build up for each spatial frequency a map. So we get such a map of strengths of all these spatial frequencies of the object. Or we get a map of Fourier spectrum of our object. So this looks complicated, but it's possible to actually get out of such a diffraction pattern, you are able to reconstruct an image. What I forgot to mention here is that, okay, so this was just the first part, actually. So we get this map of all spatial frequencies, as I said, and now we have to reconstruct an image out of it. So to do that, yeah, we need to actually align all these frequencies in such a way, all these patterns in such a way that they will properly interfere to form an image. And that's not easy, because the information to tell us how this alignment should be done is not, present here in a way that we can encode it easily. It's hidden in the phase of the diffracted beam, and this is a well-known phase problem. So it's a pursuit of many crystallographers trying to figure out how these patterns need to be aligned to each other to get an image. So, but yeah, what I wanted to say is that it's possible to be done. This was done on this diffraction pattern here, for example, for short wavelengths. This is reconstructed image of this diffraction pattern that doesn't, it's hard to interpret like just looking at it. Of course, nowadays we have powerful algorithms and computers to do this kind of work. It is much easier, if it's possible, to actually, instead of doing what I was just saying, to basically collect the light that comes from this object and reconstruct or reinterfere it here into an image by using a lens. This is actually how a simple microscope works. So, so this is again the same thing. We consider each spatial frequency like before. So the object acts as a grating. It diffracts light along two different paths, and then the lens, in this case, functions as an interferometer and interferes light to form an image here. So the finer are these periods in the object, the largest are these diffracted angles here, and the steeper the angles that reconstruct and these waves here. So we get a finer period also in the image. That's all fine. We can do that. However, the only problem is that there's no one yet that made the atomic resolution lens. So that would be the easiest. But maybe you might ask yourself, how was I able to show you atomic resolution images at the start of the presentation if there are no atomic resolution lenses? Well, we are utilizing a trick that was discovered soon after the discovery of X-rays. While, for example, Röntgen, who discovered X-rays, became really frustrated by analyzing different materials, trying to figure out well, which materials reflect or could be used to reflect or focus X-rays. He came even to, I read that he said X-ray lenses and mirrors are not possible, to this conclusion. On the other hand, well, another German physicist, Max von Laue and his colleagues, demonstrated that, actually X-rays diffract off single crystals. So it's a trick, as I said, because you need to have crystals. So they actually took the first X-ray diffraction images here. So this is an X-ray diffraction image of this natural crystal called zinc sulfide, which actually grows as in a pyramid, like a pyramid. It has so square, 4 symmetry axis, facet here on the bottom. So this is the 4 symmetry that we see from this diffraction pattern, and while the sides are triangles. No? So we have 3 axis fold symmetry here. So from these images, it already became clear, so they already learned that crystals, which they already suspected have periodic structures of atoms, really have periodic structures of patterns, and that they have certain symmetries. However, Max von Laue was not able to interpret these X-ray diffraction patterns in the sense that he was able to say what is the structure, exact structure of the crystal, so something like this at that time. It was actually a team, father and son team, Lawrence and William and Lawrence Bragg, that finally cracked this problem. So basically Lawrence Bragg realized that the key to the problem is that X-rays reflect off these planes of atoms in a crystal, and that if he can figure out, so that he has to figure out where do they scatter, and then sum all these rays of scattered rays that go in this direction. So he was able to actually connect the distance between the planes of atoms in these crystals, which is called here D, with the wavelength and with the diffracted light, so the diffracted spots that he saw in the diffraction patterns. So this is Bragg's law. And well, just to explain a little bit how do we derive this law, I'm showing here 2 rays that are interacting with these 2 planes of atoms here in a crystal. And you see here that the bottom ray is slightly longer than the top ray. And this path difference here that we see, so incoming and outgoing ray, is equal to this space in between the 2 planes, this D. And from geometry you can realize that it's equal also to the sinus theta, so where theta is the angle at which X-rays impinge on the crystal. So you have to multiply that by 2 because we have incoming and outgoing here path. And as long as this path difference is equal to 1 wavelength or 2 wavelengths or any whole number of wavelengths, then these 2 rays, outgoing rays, the top and the bottom, are in step. So maxima are aligned here and minima are aligned. So as I said, you have to add these rays, and when you add them, you get twice as large rays, so increased intensity, and this is called constructive interference also. So if this difference, path difference, is different, let us say 1/2 of the wavelength, so here, then we see that the outgoing rays, like the maximum of the bottom and the minimum of the top ray, are in the same position. So if we add these 2 rays, obviously we cancel actually all radiation or all scattering going in this direction. We don't get any radiation in this direction, and it's called destructive interference. So Bragg worked on diffraction patterns, or solving diffraction patterns in crystals that occur in nature first. So here are shown few nice examples of quartz, iron pyrite, calcite, and so on. There is a limited number of crystals that you have in nature, but people soon realized, that it would be great to use this technique also to, look into things that are also very small on atomic scale for some in some other examples. And they started growing protein crystals, among other things. And here I'm showing an example of a diffraction pattern of a protein crystal called photosystem 1, which is one of the proteins involved in photosynthesis. And as you can see, this diffraction pattern looks much more complicated than the one that I showed initially of a single crystal. However, it's the only way to actually get information how the proteins look like if we take X-ray diffraction patterns like this. So for this we need actually to grow relatively large protein crystals, which is a challenge. It might take years. Actually, photosystem 1 is an example which probably took more than 5 years for sure to grow a crystal large enough that could be analyzed with the powerful X-ray sources. So, why are we bothering growing protein crystals if it's so difficult? Well, the reason is if we are shining X-rays on one single molecule here, we get a diffraction pattern that I showed before, but the signal is not sufficient to actually do much with it. So if we take a crystal, so instead of having one molecule, we have several that are actually also distributed in the same fashion as atoms in natural crystals. So instead of atoms, we have now molecules. And the signal, of course, will be enhanced, will be proportional to the number of unit cells. So we want to have a crystal to enhance the signal. The information that we actually get, the diffraction pattern, is reduced as compared to the previous one. We only see Bragg peaks, but these are huge. They are very intense, and we can do something. We can reduce the structure out of this. So to do X-ray crystallography on protein crystals, we therefore need large crystals, relatively large crystals, but we also need very intense X-rays. So like such intense X-rays come out of the synchrotron. I'm showing here two examples. I chose this one because I am working at DESY, so this is Petra 3 synchrotron, and Electra because it's very near here in Bazovica. Both of them are state-of-the-art synchrotrons. So this top one is optimized for hard X-rays, and the bottom one for soft X-rays. And there are many synchrotrons around the world, and I think the majority of the beamlines probably is being used for doing protein crystallography. I think it's really very important for protein crystallographers to use the synchrotrons. So what next? What I wanted to say is, however, even though these X-ray sources are so intense, there is a limit of what we can see with them. Here I'm showing what's happening with the protein crystals here. Protein crystal where we shine X-ray light, for example, in this position for 1 second. So you see it's destroyed. Wherever we shine, within a second, the crystal is destroyed, even though the dose is not so large. Actually, the dose is, in this case, only 1 X-ray photon scattered off per molecule. So this basically forces us, so this dose, so the limitation of how much dose we can actually put on such fragile protein crystals, forces us to use relatively large protein crystals. So typically they're on the order of 100 micron, which of course it's not easy to grow and purify and grow. And it's a major bottleneck for protein crystallographers. So this is really a problem. So one counterintuitive idea how to overcome this bottleneck is to look for even more intense X-ray source than the one that I was just presenting. And in this paper, it has been proposed that X-ray diffraction of very tiny crystals, or perhaps even single molecules, could be obtained if one has very intense and very short X-ray pulses. So we can see here what is happening as a function of time with the molecule. So after it has been hit by such an intense X-ray pulse. So these are simulations. We see that it takes a while before atoms start moving, and even atoms that are very small actually have inertia. So it takes some time that they start moving and explode basically at the end. So we have this time window of about 10 femtoseconds where the molecule is still as it was originally, so pretty much intact, not damaged, so to say. Well, I'm plotting here a quantity called peak brightness, which is associated with different X-rays, with X-ray sources as a function of time. So we see that this peak brightness, and this y-axis here is logarithmic, is increasing exponentially over time. So with the advent of synchrotrons, for example, there was a big jump in peak brightness, and now we have free electron lasers where this peak brightness really went up. It is a quantity that's basically, shown here in very strange units, but basically tells us how many X-rays do we get out of the source per second, how large is the source, how does the beam propagate as it moves and spreads out, and what range of photon energies contribute to the intensity that we are showing here. And this is exactly the quantity that we care about when we try to determine what a tiny crystal can actually sustain before it gets damaged. So as I already said, free electron lasers are at the forefront of the brightest X-ray possible sources available. So shown here is FLASH, which was the world's first free electron laser. That's at DESY, and it became operational in 2005. I'm showing here again an example here from Bazovica Fermi at Elettra, which is the first seeded free electron laser. There are not so many X-ray free electron lasers in the world, but we are involved also in building European X-ray free electron laser in Hamburg together with other European nations, which will become available in a couple of years. So these are very large and very expensive facilities as compared to synchrotrons, which have this ring form structure and can serve many users at a time. These are linear structures, extremely long, several kilometers long, and they usually can serve only one, maybe potentially two experiments at a time. So here we are seeing a tunnel of linear coherent light source, which is at SLAC, so in California, the hard X-ray free electron laser, and we see part of an undulator, which is a periodic arrangement of magnets, basically 132 meter long. It is just part of this tunnel, extremely long tunnel. So, let me just briefly describe how do we create these very intense and very short X-ray pulses in these free electron lasers. This is SASI principle in this case. So the electrons electron bunches that come out of an electron gun move through these accelerating cavities. So these are structures that actually are kept at very low temperature at minus 270 degrees Celsius, so that they are actually behaving as, so they are superconducting cavities. And in these structures, electrons get accelerated to basically speeds close to the speed of light, and also their energy increases a lot. You see this, as I said, this is part of this really long tunnel, in this case about 2 kilometers. And when they reach these really high energies and very high speeds, electron bunches then enter into several undulators, where undulators, as I said, are periodic arrangements of magnetic magnets here, where south and north are alternating. And these magnets, an undulator forces the electron, because it has a charge, to slalom, so through this undulator. And whenever electron is changing the path, basically loses X-rays, loses its energy in the form of X-rays. So these X-rays then move faster than the electrons, which are forced to slalom through the undulator. And so while electrons go slower and slalom here, X-rays move faster and start interacting with these electrons, and then eventually start interacting with them in a way that they, speed up some electrons and slow down the others, so that these electrons start forming such disks like you see here, but they are still, of course, emitting X-rays, and but they are emitting X-rays in synchronization, and this basically then comes out as very intense and very short X-ray pulses. Well, just to schematically show the difference between X-rays coming from a synchrotron and from free electron laser, I'm showing just this schematic picture here. You see that X-rays coming from free electron laser are much more intense, but also much narrower. So the time, so the pulses are only 30 femtoseconds long, and for most of the people, this is kind of an unbelievable, or maybe not even understandable time. But femto is 10 to the minus 9, but maybe it's better if I explain it like more in a term of how many femtoseconds go into 1 second. It's kind of the same as how many seconds go in 31 million years, I calculated approximately. So that's the time, short, so this is really short time. So I said that, so X-ray free electron lasers may enable us to do atomic resolution imaging of very tiny crystals or even single molecules. So this is basically our dream experiment. So we have here a very powerful X-ray laser. We shine this laser on a molecule. So we are bringing molecules one at a time in a stream of this molecule. And then we collect diffraction. So this is all fine. However, we still don't have enough intensity, even though I just said that X-ray free electron lasers are the most intense X-ray sources in the world. They still don't have enough intensity to be able to give us measurable signal from such small single molecules. So what we have to do is, try to collect as many photons as possible from the source, from the source, and then in addition, we would like also to compress this pulse in time, which also increases the intensity. So, as I said, we would like to focus X-rays further because we don't have enough X-rays on the molecule, and we would like to compress it in time to increase the intensity. And we have to make sure, of course, that this all lands on our molecule. So to do this, we can use X-ray optics, multi-layer based X-ray optic. So multi-layer optic, usually, it looks like that. It's reflective optic, a coating that you put on a substrate. So if you cut it in cross-section and looks just basically on the thin coating that you have here, under very powerful microscope, in this case this was done with transmission electron microscope, you would see that it consists of periodic structure with such very thin layers, where these layers are on the order of a nanometer or so. So maybe you can now already see that there are some similarities between these layers here and atomic planes in a crystal. And actually, multi-layers are artificial crystals. So we're not limited just to the crystals that exist in nature, but we can basically tailor and make a crystal as we want. We can decide which materials we put down, how thick these layers are, and so on. So as artificial crystals, obviously, these multi-layers also obey the same Bragg's law. So we have similarities here as well. And X-rays basically reflect off these interfaces where we have the largest gradient between the two layers. So one is usually lower density and the other one higher density material. And we have to ensure that these interfaces are as sharp and as smooth as possible to get high reflectivity optic. So, yeah. So to focus X-rays, we can do this, for example, in these two ways. One way would be to use a shaped substrate. So the substrate can consist of glass or single crystal, and coat it with a multilayer. So this is Kirkpatrick-Boas lens or mirror set, where one mirror focuses X-rays in one direction and the other in the other direction. So it's pretty common actually to be used at synchrotrons, but also at free electron lasers. And the other one is to shape the coating itself, the multilayer coating. We can do that in lateral and vertical direction, basically in both directions. And we can form things like volume zone plates. So zone plates are usually made with lithography, but we can make also thicker and very precise zone plates that work also for hard X-rays. So these structures are much smaller than this here, but they enable us also to focus X-rays to much smaller dimensions. So, one of the applications of the multilayer optic is actually imaging of solar corona. I mean, there are different applications. I decided I won't show application of extreme ultraviolet lithography in the industrial project this time, because I showed this picture before. I just wanted to say, of course, the sun is very important for us all. It's giving us energy, light, and we know that the sun output is changing over time. There are cycles that are 11 years long, but then also there are changes that happen, all the time. And as we are getting more and more dependent on things like satellites or GPS and so on, these changes of sun's output are quite important to us to understand. And this is enabled basically with telescopes that carry optic that is multilayer coated and are orbiting the Earth. So how do we actually make these multilayers? I'm just having one short slide. Just wanted to say we use vacuum machines in which we place the substrate on which we want to deposit this coating. We have inside materials we want to deposit. We form plasma, and then we basically move our substrate between the two materials of choice with very high precision and accuracy. Basically, we can do things that are much more precise than any other method that you can use, basically. So, for example, the layers that we're making can be only several angstrom thin, and as compared to what you can do with lithography, for example, that's a factor of 40 better than what you can do with lithography printing, I don't know, microprocessors or integrated circuits and so on. So here is an example of our, such structure. It's part of this volume zone plate. That this is basically state-of-the-art, what we are doing right now. It's called multilayer Lowry lens. It's a three-dimensional structure, rather small as you can see, where we, first deposited a multilayer that's rather thick, overall thick, rather thick, consisting of thousands of layers, which are, as you see, very thin if we zoom in, and then shaped in the third dimension with focused ion beam, which is a nanotechnology tool. So such structures then enable us to focus X-rays, and I'm showing here just a setup that is very similar to the one that we used just recently. We've done the experiment at Petra 3 just a couple of months ago, and we are still evaluating the results. But it was very similar that we used a multilayer Lowry lens that can focus X-ray in one direction. And of course, there is still to do that we have actually a set of these two multilayer Lowry lenses, so focusing in the other direction. And this group also used as a sample another multilayer with a larger period here in this case. And they were able to demonstrate a very good result. They got actually 11 nanometer focus in one direction and were nicely resolving the structure. So our results are still preliminary, but I can just tell you that they are better than this. And we were also working with much harder X-rays. This group was working at 12 kiloelectron volts, and we were doing experiments at 24 kiloelectron volts. So, well, when you put X-rays into the free electron laser, well, what's happening to them is that basically pretty much always they get completely destroyed. So this is the experiment that Professor Archon mentioned at the start. It was done, yeah, this was the very first experiment done at soft X-ray free electron laser at DESY at Flash. So we had a structure like that. This image was taken with a secondary electron microscope, and we obtained with the very first shot this diffraction pattern. So, well, since this was like pioneering work, no one knew what to expect. So we shot again, and the diffraction pattern looked like that, obviously different. So we looked why, and yeah, there was no sample there. There was just a hole. Basically, within few femtoseconds, whatever it took to do this one shot, sample evaporated, turned into plasma. Nevertheless, what was important, of course, is that from this single diffraction image, we were able to reconstruct the picture again. This is a reconstruction, which looks, as you can see, very similar. So this was a proof of principle experiment, still done at relatively long wavelengths, so we don't have atomic resolution here. It was still on the order of, so the experiment was done at 32 nanometers, but it demonstrated a very important thing, that we actually were able to obtain X-ray diffraction before destruction. So it's so-called, now everyone uses diffract before destruct concept. So it demonstrated that, but also opened completely new field of coherent X-ray diffraction. And what's also very important to show is, of course, that this particular experiment, and also many more after them, was enabled by multi-layer-based optic. In this case, multi-layer optic was not used to focus the X-rays, but was used as part of the detector. So we are here basically reflecting the scattered light from the sample into the detector, and very nicely filtering the signal as well. That was very important as well for this experiment. Well, another way of increasing the intensity, in addition to focusing that I was just talking about, is to compress the pulse in time. Classically, this is done with gratings that send the path, the beam along different paths here for different wavelengths. Well, in X-ray free electron lasers, it is possible to create so-called chirp pulses, where actually the wavelength varies along the pulse. So here we have longer wavelengths here at the start of the pulse, and shorter wavelengths at the end of the pulse. So if we send such a beam, such a chirped beam, along this path with longer wavelengths at the front, along the longer paths, and the shorter, so behind, on the shorter path, then the tail will catch up with the head, and we will compress the beam, and this is what will happen. It's compressed in time and more intense. So again, this is very, very nice idea. However, to do this with X-rays, you need gratings with very fine grating pitch. So again, in this case, multi-layers come to help us because we can create artificial structures that actually enable us to do this, well, something that, you would not think it's possible. So we take a rather thick multi-layer and we cut it like that. And so this is so-called asymmetrical cut multi-layer. And due to the boundary condition here, this multi-layer that was before just a standard reflecting mirror acts now as a grating. Here I'm showing also an image of a real cut multi-layer, just to demonstrate that we can get good quality asymmetrically cut multi-layer. Actually, we are getting ready within a couple of months to do the experiment where we want to demonstrate that the pulse compression really works. So you can see this here. We've demonstrated, however, already on a symmetrically cut single multi-layer, single asymmetrically cut piece, that it really acts as a grating. So that was already done and it's published. And you can see here on this plot I'm displaying here wavelength and detector angle. So if we shine X-rays at a fixed angle onto this asymmetrically cut multi-layer, if we see this behavior here, this is a behavior of a standard mirror. So no matter what wavelength do we have, the reflected light always comes back at the same angle. So that's the reflection law. However, in this case, this line here, which are also measurements and the fit that matches the grating equation, we see that if we change the wavelength, if we're changing the wavelength and keep the X-ray angle, angle of the X-rays impinging on this fixed, we actually have to move the detector to actually see the maximum. So it behaves like a grating. So with this very intense and short pulses that we can get out from X-ray free electron lasers, we demonstrated that we can actually get atomic resolution images from rather small crystals here. So these crystals form around a virus called granular virus to protect the virus itself, and they consist of only 6 unit cells per crystal. So this is very small amount when you think that you have to do something with it, to try to reconstruct the structure out of it. So, well, for a comparison, so in volume, this crystal is 1,000 times smaller than the smallest crystal ever, ever measured at the synchrotron from where you were able to reconstruct the image from. So it's really a big step forward, and we were able also to obtain the structure of this crystal with 2 angstrom resolution, which is also pretty good. So this type of experiment basically also gave us a feeling or a way to determine how far are we to get single molecule imaging that I was talking about. So we estimate based on this experiment that we still need a factor of 6,000 of intensity to be able to do single molecule imaging. Well, you can look at it from 2 different points, like either it's really still a lot, but on the other hand, considering what I was just talking about, X-ray optica that can enable you to focus X-rays to such small dimensions of 10 nanometers or less, as compared to the beam that we typically use now, which is maybe a micron, it seems like this goal is feasible. So we need probably about 10 to the 14 photons per micron square, to achieve this goal. And so I would like to finish my presentation with this slide, which actually shows our dream experiment again. So we would like to have extremely intense X-ray pulses here, which we can further focus with optic that I was describing or compress. And then we have here, we are shining these X-rays onto a stream, micron or submicron stream of nanocrystals, or, well, eventually maybe single molecules, and collect these diffraction patterns and, of course, reconstruct them. So the fact that we can actually work with nanocrystal is already a big step, big improvement as compared to the traditional crystallography. We can actually work with nano-sized crystals and resolve their structure, and this opens up to study many proteins that don't like to crystallize at all. There are certain proteins that don't like to form crystals at all, but they might form a few nanometer crystals, which are still already very useful for us. So, and finally, I would like to thank members of my group, current and the ones that maybe already moved further, and Henry Chapman, and of course also all of you for listening here. Thank you very much.
Well, thank you for the nice presentation. Maybe we sit down and have a short discussion. For the beginning, And for warming up, some questions from my side, and then we give the possibility also to audience to put some questions. One of the things, of course, which was here interesting is your dream experiment, where you mentioned that you do pulses individually. Of course, one shot destroys the sample, so you need a lot of samples, because otherwise this machine would give one pulse and then 1 week of doing nothing.
Yes.
So what is typical frequency, and how you plan to prepare many samples in a repeatable way?
Yes.
So
yeah,
the idea that we, in a way, also collaborate with...
Yeah, so the pulses come, well, depending on the source. Now, for example, the source in California at LCLS has a frequency of about 100 hertz. But the upcoming European XFEL will have much higher frequency. We are trying, of course, to match the frequency of the pulses with the samples. So we are developing ways of being able to synchronize these two, so the X-ray pulse and the sample some way. So I'm working also on that. Of course, we are working on all kinds of ways to minimize the waste of this material, because we are working usually with materials that are very hard to prepare. As I said, growing and purifying and growing these crystals is hard, but also preparing large quantities of proteins of interest is also very time consuming. So we are trying to develop different techniques that would enable us to synchronize the frequency of the pulses with frequency of our samples, and to minimize waste. Also, of course, to make the beam as small as possible of the liquid in which these samples are as small as possible. This is also associated with the development of these nozzles, for example, that spray in our sample, and so on. Okay, so but as I understand, here's quite a lot of, let's say, scientific work, but directly connected with high technology. So in a way, how you combine, do you have a good feedback from the companies? Do you also boost the development in the companies, so collaboration with industry? Do they feel in a way that this kind of science is also promoting industry and making new products? Yeah, well, in particular, this type of research that I was showing is, of course, of interest more, for pharmaceutical industry, for example, development of new drugs and so on. But from the instrumental part of view, I think, that's maybe, we don't have so much connection with industrial partners. So you develop yourselves all the optical things? Yes. Yeah, but in principle, when you patent this, it can be used for many purposes. Yeah, sure, yeah. So, for example, the development we are doing with the nozzles definitely can be used also in other applications. And well, you mentioned also in telescopes or optics for different things. So it means that it's something that will bring a lot of, let's say, high-tech development also for others, not only for macromolecular scientists. Yes, yeah, okay. So maybe one thing is what I'd like to point out is that maybe you should mention how the things are developing now. There is a lot of investment. All this equipment definitely is very expensive. XFEL, it's not so cheap thing to run. Yeah. So how do you feel it in your institute? What's happening there? I know a lot of things are being built at the same time. Where does the money come from? Who decided for such an investment into science? Yeah, so, the work that we are doing is pretty much funded, funded by the state, primarily by the state of Germany. More than 5 years ago, basically, or maybe 8 years ago, when they decided, that Germany decided, or maybe saw that harder times are coming, they decided that they want to invest much more in technology and science to become competitive, and as competitive as possible in the world. So they basically invested lots of money in building the facility like Flash, but also to found a center, the Center for Free Electron Laser, which basically started 6 years ago when, well, we came there with my husband. We were the two very first employees at this center. And if you go there now, you will see about 300 employees in this short period of time. I think, yeah, doing all kinds of science projects, not just biological imaging that I was talking about. So I think that was a very nice decision that they made these long-term commitments, and even though then the crisis came also in Germany, the money was already committed, and they followed that and used it for these purposes.
So this probably is also very attractive for young people. Do you get people locally or around the world?
Yeah, actually, well, it was a big transformation of DESY. DESY was, of course, traditionally a particle physics laboratory. Well, I would say in the last 5 years there were huge changes. Actually, interestingly, also in the same, well, brother laboratory at SLAC, which, well, both were doing similar things before in particle physics, and both now are doing similar things in photon science. Well, you can come to Hamburg and go into the center, our center, and you see that there are lots of young people coming from all over. I mean, at the start, we were a little bit concerned because, no one knew about it, and but now there's no, it's really attractive place for people from all over the world, because traditionally, I would say, people would always go to US to gain more experience, and that's, of course, still a very desirable place to go and do work there. But definitely, in the meantime, I mean, really everyone acknowledges that Hamburg is like really a world center. I mean, having soft and hard X-ray, the free electron laser, and so on, facilities in this field.
Maybe, is there a question, or there are questions from audience? Yes, please. Yeah.
Two questions. One very simple. You mentioned European X-FEL. Is there Slovenia involved in the construction?
Okay. Unfortunately not, although I know that there were some individuals that expressed interest to get involved, and I was even involved in talking to the director of European XFEL, who was wondering if the government would be supporting something like that, and unfortunately it didn't happen. However, like among other countries, also Slovakia is involved, and Slovakia is actually involved in European XFEL and another project that we are actually building a special instrument in, so seems to be investing more. I mean, okay, it's slightly larger country, but not so much larger.
And then about these multi-layer coatings, which materials you like the best for giving these nice interfaces, and how sensitive, how many pulses can they survive under the X-ray radiation? Thank you.
Yeah, okay, so materials really depend on what the optic has to be optimized for, so which wavelength they have to work at. So I can't tell you, I mean, it's almost everything in the periodic system that you can actually deposit. Well, I'm trying to avoid toxic materials and so on. So we try to, of course, protect X-ray optic from being destroyed. So the optic that I was showing was not placed usually in the focus of X-ray free electron laser. We realized that if it's not placed in the focus, but away from it, it actually survives, like the optic that I was showing to reconstruct the very first X-ray diffraction pattern to get those two cowboys. That one we used over and over, and the only problem we had was carbon contamination, because there's always some hydrocarbons in the vacuum, even though the vacuum is very good. So, but yeah, if you put it in into the focused beam, which is another experiment where we also do, then you have to live with it that one single pulse makes a crater in it. Yeah, so.
Yeah, thank you. Maybe another question? Yes, please.
Would it be of some improvement if you could shine the pulse of light on a sample from several directions simultaneously, no? So that, or you can deduce the three-dimensional structure from one direction.
Yes, yeah. So these are actually thoughts along, or even some experiments already planned in this direction. So this is so-called stereo imaging that, yeah, definitely. How to implement that is a little bit harder. It's harder to implement, but yeah, I think maybe even some collaboration at Fermi, we were discussing something like that. Yeah.
Yes, please. You have a microphone?
In one slide, you show that in Petra you have hard rays, and in Electra you have soft rays.
Excuse me?
In one slide, you show that in Petra you have hard rays, and in Electra you have soft rays.
Petra is it's hard rays,
yes.
X-rays, and Electra is soft X-rays.
Yes, yes, yeah.
So soft rays means low energy rays.
It's okay.
I'm not sure I understand.
Soft rays means rays which have low energies.
Yes.
Soft X-rays means yeah, lower energy. Yeah.
UV and soft X-rays.
So it's several, well, like 100 electron volts or several hundred of electron volts, while hard X-ray means kilo electron volts or higher, 10 kilo electron volts.
So that's why this Electra means this system is circular to make soft rays. Less
no, synchrotrons in general are always circular. Also Petra is also circular. Yeah. I can.
Okay, you can discuss. It would be easier later on.
Yeah.
Is there maybe another question? Well, if not, we'll come to a conclusion.
Yeah.
I would just invite everybody that we, after the lecture, move down and have a possibility to talk with our guest also in private, so with a glass of wine. And let's thank again for a nice lecture. Thank you.
Yep. Thank you very much.